Yes, thank you. Oh, okay, nice, thank you. So, hello everyone, I'm Balázs. Yes, thank you for the introduction from Gergely. So, just the first question: is this better if I speak like this, or is it better if I speak like? Okay, okay, sorry. Okay. So, um, so this topic I would like to talk about is pretty much a work in progress topic still. So if you expect uh, some finished results, you won't get this currently, but maybe in the near future. So I already talked about this topic in the previous GPU days, and I would like to, now I would like to talk you about. Uh, so first of all, this topic is of computational simulations. And because it's also like related to cosmology, I would like to talk about cosmology first a bit, just for the record, and then move on to the computational part of this entire topic. And so as I said, it's a work in progress topic, and I would like to talk about, as I said, about cosmology first. So as you can read on the title of the first slide, the science that tries to describe the universe as a whole is quite a bit of a mess now. And uh, uh, not just nowadays a mess, actually, as the title said, but for the past couple of decades, the situation worsens basically year by year. And physicists in the room are well aware of all these problems, and they can recite these cosmological problems even in their sleep. But for those who don't know, cosmology suffers from many problems, and one of the most notable and most widely discussed and I don't know most widely popularized problem is probably Hubble tension. So measuring the expansion rate of the universe is actually yields us two very different values depending on the method used to measure this value. And these two values are far beyond the error bars of each other. So you can actually see the evolution of these measurements over the years since 2000, how they diverge from each other into these two different values. And you can also see the third one, which is not relevant for now. And I just put up some other illustrations here to show that cosmology is very problematic. We are problematic people, and we have to deal with it. And that's why now in the era of precision cosmology, where even a 1% error is too huge to bear and deal with, we need to somehow address all these problems to move forward somehow. And the current situation looks something like this. We have many competing models and theories that tries to describe one or two or I don't know, all of the problems and observations and tensions at once in cosmology. And if one of the ideas is intriguing enough, and it gets published in one of the better journals, and maybe the media picks it up, then that will make people to talk and think and investigate. And yeah, they usually talk before think, but anyways, so among the zoo of ideas, in this context, uh, uh, was this paper published recently, and some of the authors you may recognize the names. They have very long names, so I had to abbreviate because it would be actually very long. And instead of, I don't know, finding or adding new tweaks to inflation or gravity or introducing anti-gravity or something like that, they took or stumbled upon a pretty old but pretty unexplored idea that what if the universe had a global rotation? That was the idea. And the idea actually comes from the simple observation that everything in a universe rotates. So from very small particles to the largest astronomical objects, everything rotates. And in fact, it was very famous physicist George Gamow who first proposed this idea in 1946. And he said basically that of, uh, of uh, maybe the rotation of galaxies could be explained by a rotation of the universe. Now we know that is not the case, just for the record. So the rotation of the galaxies mostly correlate with the rotation of the dark matter filaments they are in. But this was the idea back then. And but anyway, we might ask, what would happen? What would we see? What would we observe if the universe had some rotation, whatever that means actually. And in a regular isotropic spherical universe, so what we are usually used to in cosmology, the expansion rate of the universe would be basically uniform. So every direction it would be the same, and that's how cosmology currently stands. But in a rotating universe, we would expect an anisotropic rotation. So the size of the size of the what did I say first? So the size of the expansion rate would be different in different directions on the sky, and basically what would it cause? Like the universe, instead of being spherical, it would be shaped like an oblate ellipsoid, basically. So and that's the most notable theoretical prediction of a rotating universe model. And this was one of the reasons why these authors calculated these values in both a spherical and in a cylindrical geometry. Uh, because if the rotation is too large, actually, the spherical model is not adequate to basically model this rotation, and the cylindrical geometry is needed. Actually, the reason for that is because these different expansion rates, their dependence in these random arbitrary directions becomes pretty complicated, and we can effectively model this instead in a cylindrical model. So, okay. So you can determine the expansion rate. That's nice. That's one thing. But in a well-formulated rotating model, you can actually calculate other observables as well. And uh, the authors of this paper actually determined that the Hubble tension could be or like might be explained by the rotation of the universe, given that the angular velocity is close to its theoretical maximum. Uh, and this theoretical maximum, this limit, is actually determined by general relativity and various observations. And they calculated the current day maximum velocity of rotation to be one full rotation every 500 billion years, which is, well, considerably so. But anyway, because a core question of modern physics got, I don't know, a simple and elegant and nice new explanation, and because it was published in a high impact journal and things like that, it made the interest in this topic explode in the recent weeks. But then everybody cried out in unison, where are the simulations? How can we trust an idea in physics in 2025 if there are no simulations? And that is exactly what we're trying to address here, and or in the progress of addressing. But why would people even ask for this? Why cosmology would need some kind of computer simulations? And unfortunately, the answer to that is quite boring and quite common in physics, simply because the equations that govern the large-scale domain of cosmology are highly nonlinear. So you can, of course, put newer and newer and higher order terms in the perturbation theory and, I don't know, calculate forever your equations. But it's very early, the computation, the complexity of these computations will explode before you even reach the necessary accuracy you want to reach. So after some time, after some very early point, numerical simulations will be the only way to move forward. Analytical calculations could describe the background of these things very well, but then to describe the formation of galaxies or galaxy clusters or dark matter filaments, you need simulations. You can't do it otherwise. So, okay, so have to imagine simulations in cosmology. What do I even mean by simulating the entire universe? And the principle of that is quite simple. So you basically start from from some initial conditions, which represents a finite box of particles which represent some early state of the universe. And by early state, I mean that the matter distribution and the velocity distribution in the early universe. And then you solve the necessary equations and evolve this system over time. And usually you evolve this system to the current day until now. And you get these kind of like, you can see the evolution here. What you can see is basically like these dark matter filaments forming in the universe and making this cosmic web. These are, you can see many famous images on the internet that looks like this. This is what they usually show you. And after that, we measure some kind of properties of this final matter and velocity distribution, and we make some educated guesses using that. And but at the end of the day, unfortunately, what we have is just a finite box of particles, which is, well, it's definitely smaller or less than the entire universe. So how can we solve this issue? What we did in the past 50 years, basically, is to take that box and repeat that box infinitely many times in all directions, on all faces of the box, which is what we call periodic boundary conditions. And this is actually equivalent, these periodic boundary conditions of a box or a box with periodic boundary conditions, to the surface of a torus. And after that, we had this configuration in this infinite grid. We solved the necessary equations, which is actually simply the Newtonian gravity. In the context of cosmological simulations, we use Newtonian gravity and not general relativity as many people would expect, because cosmological simulations usually deal with this low velocity, low gravity limit of physics, and Newtonian gravity is a perfect approximation to work with here. So this approach, this periodic boundary conditions, both has its advantages and disadvantages. But what I want to emphasize, and there is only one thing that matters for us here, is that a rotating universe cannot be simulated this way. Because a rotation, you can do anything. A rotation on the surface of this torus would it would appear as a constant velocity flow on the surface of the torus, which means it won't have any kind of acceleration as you would expect from anything that rotates. That, like, whatever rotates, it should have some kind of centripetal force in it or any fictitious force, whatever, but this does not happen. So fortunately, there is another way to simulate or use boundary conditions, which based on a very simple idea, which is actually was known by the Greek philosophers as well already, the ancient Greek philosophers, and it is stereographic projection. And what stereographic projection does is, in general, is it creates a map between the surface of a sphere and the entire infinite plane. So every point of the sphere or the surface of the sphere corresponds to some point on this infinite plane. And you can actually generalize this to higher dimensions, what we do here using a special simulation code called STEPS, which stands for stereographically projected simulation, cosmological simulation, something like that. It has a long name. So the way that STEPS realizes this stereographic projection in higher dimension, that it basically creates a map between the entire 3D space, so basically the entire 3D universe, and between the surface of a 4D sphere. So it's basically just one dimension higher than the regular stereographic projection. And due to the geometrical nature and geometrical properties of this projection, the simulation in this 3D space will have a varying resolution, as you can see on this bottom right image. Basically, particles farther away from the center will correspond to larger masses and larger volumes in the universe until basically the outer region corresponds to the entire infinite universe beyond some cutoff distance. And yes, it is actually much closer to physical reality to simulate like this, because like the periodic boundary conditions with these various cutoff radiuses in the force calculation, this is very arbitrary, and they were employed due to numerical limitations in the future and due to numerical convenience, but it is actually much more physical, and it's really cool. And so we, in the past, we made uh, uh, spherical simulations. And as I mentioned, like the most notable effect you can measure is the expansion rate, or the discrepancy of expansion rate of the universe in different directions. And so we simulated these, or made these simulations in a spherical geometry and measured the value of the expansion rate parallel and orthogonal to the rotation axis of the universe. So in two different directions. And this is actually not a trivial task, because like when normally physicists calculate the expansion rate of the universe, they do that in the isotropic case, so for every single particle in the universe all at once. And this is pretty trivial. But to measure it in two different directions and do it in a physically and numerically and mathematically meaningful way, we had to invent some plausible method to do so. And we came up with something. I won't detail it, only if someone asks. And and what we got is actually that we approximately got what we expected. So we were able to measure or simulate and then measure this anisotropic expansion in the way we expected. And that's what you can see in the left side and in the center of the figure, basically in the uh, orthogonal direction, the expansion is faster than in the parallel direction. But on the right side of the figure, you can see that why this paper was kind of inconclusive, or it was maybe, I would say, it was conclusive about that we need a cylindrical simulation instead of a spherical one, because the difference between these two directions didn't reach or didn't converge to the expected value, what we expected from the model. So we're trying to make cylindrical simulations, and it is currently what's working in progress. And it is much more challenging than it seems. And I was thinking what to put on this slide, because, well, what we have is lots of different simulations that are simply bad. Like we have blobs or completely I don't know, we have bad simulations that I don't want to show. So I would just to illustrate the challenges in the cylindrical simulations using, by comparing the gravitational force of in the spherical case and in the cylindrical case. So in the spherical case, these are pretty simple equations like first or second semester calculations or derivations in any physics curriculum. That's great. But what about the cylindrical case? In the cylindrical case, we have this. Okay, this looks pretty bad, but it is not as bad as it looks actually. So you just need to sit down and type this out and write various numerical techniques to integrate these equations, but you will get what you want. And it's, you just have to sit down and do the work. Okay, now, okay. And however, there are many other problems that we face in case of cylindrical simulations, and I would like just to talk about them, just talk about these problems, what they are. For example, the most imminent problem is that we need to use mixed boundary conditions. So how we basically mimic a cylinder or an infinite cylinder in a numerical context is that along let's say along the z-axis, which is normal to the faces of the cylinder, we repeat these simulations normally as we would in, I don't know, a regular periodic boundary conditions or simulation with regular periodic boundary conditions. And the other two dimensions, in the x and y dimensions, we use stereographic boundary conditions. So this needs to be implemented, obviously, because no simulation code does this. The second and third problems with the simulation is actually why we're using this abomination here in the force calculation, because there were interesting problems in the simulations we tested. So for example, when we tried to run the simulation with just a naive periodic boundary condition in the z direction, it collapsed. In very strange way, it collapsed. And we realized that we need a more well, a better periodic boundary conditions or more complicated, more complex boundary conditions. For example, some kind of inverse summation scheme that it creates other problems in the simulation. Uh, Basically that what the problem it creates that we need, instead of an infinite cylinder, we need to use the gravitational force of a finite cylinder. And as you can see, it's much harder or somewhat harder to calculate, but it will give at the end of the day the same results. And the next problem is that there are no initial condition generator code available for this kind of problem. So it needs to be written by scratch. That's what I'm actually working on. And it needs to deal with all these problems and all the geometrical properties I mentioned here. And at the end, even if we were able to create a simulation with the correct perturbations and effects we want, we still don't know whether there are some unexpected effects that will arise in the future. So basically, the unexpected effects are expected to arise. So, okay, this is also the outlook of this project. In this one, we need to solve these problems. And just to wrap up, what I talked about, the rotation as some kind of solution to the Hubble tension might be, yeah, it could be. We don't know yet. We will see what the simulations gives us. The second is that the steps was able to already reproduce uh, the anisotropic expansion in this spherical toy model. And the third one is that cylindrical simulations are coming this summer. So I hope that we will have some more conclusive and interesting results in the next GPU conference. And thank you.
Thank you very much, Balázs.
Thank you. One of the question is why would be the universe have a cylindrical shape, but it's probably just in the simulation. The other question of mine is that probably you are aware of the alternative explanations, which they call timescape, that the gravitational redshift is different in different directions because the density is not homogeneous in the universe, and that could explain also Hubble constant measurement discrepancy.
Yes, of course. So there are, I mentioned there are many other competing models that tries to explain one or two or different uh, tensions and observations in the universe. And I don't know how to answer that question. That yes, that's we are aware. We just want to test this one because this is something that can be simulated and can be simulated in a way that nobody else did actually. Nobody else made simulations anything like this before. That's why we are using. If that is your question, that if I am aware, yes, I'm aware, but we're doing this.
I'm sorry to ask a physics question, but it's very hard to imagine what is the origin of this global rotation. Because if there was in the Big Bang, then it would be washed out by the inflation. And if it is produced later, then you could see any other different scales, not just the global rotation, but all of the filaments and all of the rotation vortices which you can observe, for example, in a bowl of water. So why is this just this, or this maybe this is the simplest? But I would imagine that it could be much more complicated. If there is a global rotation, it should be much more complicated.
Definitely, and the problem is that the literature of this basically rotation is well, it's not too big. So there wasn't too many people who discussed this kind of effects, and what mostly they discussed is a very different type of rotation what we are discussing here, because this type of rotation is a shear-free, parallax-free rotation. It's basically a solid body rotation, and most of the literature discusses rotation with shear, for example, like there are a whole section in the 2018 Planck paper that describes that gives basically an upper limit for rotation of the universe with shear. And it's a very low value. So they basically say that there is no rotation of the universe with any kind of shear. But it doesn't mean that there is no rotation without shear or shear-free rotation. And what was the beginning of your question? Like yeah, it could be. I don't know. Like we considered that this is something that we basically considered that the rotation had some value around the CMB radiation, basically, like uh, when it happened. And since then, it slowed down considerably. And yeah, basically, we didn't think that, or we didn't discuss that option. That yeah, really, what we just discussing here. What if there was a rotation, regardless of its cause or regardless of its nature?
Okay, next.
Thank you. Have you heard about these very recent DAISY dark energy spectroscopic blah blah project discoveries? If it holds that the dark energy is not constant throughout the time of the universe, I'm just wondering if you could accommodate these two in your model. Or you just don't care, but definitely this will perturb the these theories behind, if it holds.
Yeah, no. It's just so. I don't want to be rude with answering the questions, because like no, these are very, very good questions, but the only answer I could give to most of the questions is that yes, we don't care many of the effects actually, because we really just wanted to see that we can simulate this kind of thing, which is, of course, it's a silly idea. What do you mean that the universe rotates? Of course, why not the universe would rotate? But we just wanted to simulate this. Basically, that was, and we wanted to see what we can get out of this. That's our only goal actually.
Okay, the last question.
So I am your uncle, according to your email. And I wonder, you're rotating matter or you're rotating the universe?
So
yeah, rotation of the universe is, of course, a different the manifold. You can do it with metric. It's a different concept. You know. So you don't rotate the universe. You rotate matter in the universe. Yeah, but as a so if you think about it, that the universe is expanding, that it's a manifold that is expanding. Okay, so all these equations, of course, create an axis.
yes, that's actually a problem, because we considered, so this is in co-moving coordinates, basically, this entire simulation. And we consider what if we could simulate it in a way that in non-co-moving, but in actual physical coordinates, where the universe is actually expanding in the simulation. And we realized that this makes everything more problematic. So we'll make one of that in the future if we could figure out how to do. But yes, it's actually complicates a lot of things.
Thank you. I have a lot of answers to you, so maybe during the coffee break we can continue because, as you know, we just opened the Pandora's box with this rotating universe. So now there's all of the things what you have asked should be included and to make a more comprehensive study.
Everybody's here,
Yeah,
actually.
and the second one coming from you. Okay,
Oh.
thank you very much, Balázs, and
Thank you.
let's switch the topic a bit.